Number chapter 16, process input and output models. Outline will talk about what process inputs are, how you represent process inputs and outputs, talk about process systems, process flow streams, utility streams, process analysis, and I'll give you an example of how all this works. Okay, process inputs are the driving force for change in a system. If you want to change an output, you either have to change the process input or equipment, and if you have an established process, it's usually really hard to change your equipment and also really expensive. Your output of your system is a function of your input and the unit performance of your equipment. When you're doing a representation of process inputs and outputs, you want to do it visually. Things you want to put in your visual representation is an overview of your process system, and you want to include process streams like your input and output streams. You want to put utility streams in there to show where your heat and work's going, and you also want to demonstrate any recycling streams. Recycling streams are really important because it alters your input streams, but you're basically cutting off or cutting into your input and output streams, and so your recycle streams pretty much affect your mass balances to your system and can also redistribute energy and stuff, so you need to pay special attention to these things. This right here is a representation of how to model your inputs and outputs in a process system. As you can see, you have your process system, then you have your inputs going in on the left, you have your outputs coming out on the right, and then you track your utility streams, your heat and work, like I said, and then you also represent your recycle streams. A process system, it can consist of a single process unit or multiple process units, usually display them linked. The process system, it performs a specific function or a complete chemical process. You don't want to start showing more than one functions because you can make it overly complicated. And if you change the input to one process stream, it can affect all downstream units and affect output throughout the entire system. So that's usually when you can focus on one area. Process flow streams are useful for performing mass balances and keeping track where everything is. Your input streams, of course, are streams entering a unit operation or process. Your output streams are, of course, streams exiting a unit operation or process. And recycle streams are considered internal streams. Like I said before, they can have a big impact on process. And there's two types of recycle streams. You have recover recycle streams, where you're basically recovering material and pumping it back through so you can continue using it. And then you also have equipment recycling. Utility streams are useful for tracking energy flow through your system, and it basically displays heat and workflow into and out of the system. This can include electrical heat and energy. Your work represents shaft work done by compressors and pumps and stuff like that, and how it works in the system. When you're doing a process analysis, you want to keep your input and output fixed, and you want to transform you want to design it so you're transforming the input into output. So you basically pick an input and then see what happens and keep your input and output fixed. You can also do process performance analysis, and that's where you keep your input and equipment fixed, and your outputs will be determined by the process system. There are equipment-independent relationships, and these are relationships that are independent of equipment specs, such as your mass balances, your energy balances, kinetics, stuff like that. And then you also have equipment-dependent relationships, and this might be like your heat transfer equation, where it's dependent upon the area of heat transfer, or frictional pressure relationship, where it's dependent upon the diameter of pipes. So these are the things to keep in mind. An example of how all this works is if, say, you need to scale up 10% the production of benzene by hydrodealkylation of toluene, and you want to analyze the disturbance by looking at two subsequent units. Here's an example of the whole system. As you can see, it's rather complicated. If you look at the left, you have a toluene hydrogen inputs. You have a hydrogen recycle stream, a toluene recycle stream, and then you have several units where work and heat, steam and condensate, and all this stuff's going in. So you can simplify this and model it through input and output streams by just finding two units that pretty much take into account all that you want. And two such units is to use the P101 and E101, because then that takes in your work, your steam and condensate, your toluene, your hydrogen, and then it'll also get your hydrogen recycle and toluene recycle streams. So you can model it. You can model it like this, and you can grossly simplify it. And with this stream, you're taking care of all your cash flows, all your energy coming in, all your recycle, your inputs and everything all coming in. So in conclusion, input is very important because, like I said, it controls your output. Your recycle streams are kind of pseudo input and output streams. They are internal to the system, and you do need to analyze these carefully. Your utility streams basically control the thermodynamics and energy of your system, and help with your mass and energy balances. And a change in a single input or unit will affect the entire system. Grossly, yeah, all this comes out of that.